There are many words to describe the fascinating vision of the night sky, where the magnificence is overwhelming, impressive, and mysterious. The human eye is limited in its ability to perceive, which leads us to depend on the most advanced technology of our era. As we know, the James Webb Space Telescope is currently engaged in the exciting work of exploring the great enigmas of the cosmos and making them visible to us. On this occasion, we would like to take a concrete look at the technical superiority of the James Webb compared to its predecessors, based on striking contrasts and new discoveries. One thing that has to be clear is that the fact that a secret of the universe has been revealed does not imply that it has been revealed in its entirety. If you enjoy our videos and want to support us, we invite you to like and subscribe to our channel to be part of this great community. When it comes to media coverage, it is common for the James Webb Telescope to be referred to as the Hubble replacement. However, based on the opinions of NASA's leading experts, the term scientific successor is much more accurate. After all, many of the research objectives that Webb is currently addressing and will address in the coming years were inspired and made possible by the results delivered by Hubble. Hubble has made a revolutionary contribution to the body of astronomical knowledge. It was logical to develop a successor specifically designed for infrared astronomy. This is because light from distant, and therefore also ancient, regions of the cosmos is shifted into the near-infrared due to cosmological redshift. Thanks to its unprecedented technical precision, the James Webb Telescope gives us the ability to glimpse the first luminous objects and galaxies that emerged after the birth of the universe, as well as the so-called Dark Ages. In addition, this $10 billion instrument allows us to delve deeper than ever into the mysterious world of stellar cradles, analyzing the chemical and atmospheric compositions of extrasolar planets in unprecedented detail. Looking at the images below, we can appreciate the impressive advances made in telescope-based space exploration in the past. Although the images produced by WISE, Spitzer, and Webb represent the same region of the sky, they could not be more different in terms of quality and detail. Although the WISE image shows merely a diffuse collection of points of light, we can at least make out something resembling individual structures. In contrast, the image captured by Spitzer shows us the sky more clearly, finally revealing its true glory. In this sharper image, we can see countless bright shapes and complex cloud structures that we could not even imagine in the previous images. Taking a look at the Ring Nebula, we can visually appreciate the beginning of a new chapter of research. This nebula, located in the constellation Carina, about 9,000 light-years away, is a colossal structure extending up to 300 light-years. The Ring Nebula represents one of the most significant stellar cradles of our Milky Way galaxy. However, by comparing the images captured by Hubble and the James Webb Telescope, we can discover how many bright secrets were hidden behind the dense clouds of gas and dust. In fact, many of the objects captured by Webb in the infrared spectrum were completely invisible in the earlier images. One notable example is the stunning image Webb captured of a protostar in the dark cloud L1527. To understand how a star forms, it is relevant to note that stars are born when a cloud of gas and dust collapses due to its own gravity. As a result, the matter in the center is intensely compressed, which causes the molecular hydrogen to break down into atoms. The protostar that forms in this process already glows, but still possesses insufficient mass to initiate hydrogen fusion. This only becomes possible when the young star accumulates additional material and becomes sufficiently dense. This development is in full progress. In the protostar, which is approximately 1,000 years old, we can observe a bright spot in the center of an hourglass-shaped structure composed of gas and dust. This stellar cocoon reveals details in infrared light, where particles and gases ejected by the protostar collide with the surrounding material. Similar to human babies burping occasionally, this manifests as bubble-like objects at the top of the hourglass. These bubbles are the result of shock fronts generated by hot hydrogen gas. As for progress in planetary research, it is perhaps the central question of our time. Are we alone in the universe? Those who examine this fascinating subject closely inevitably face another question. Is Earth the only celestial body in the cosmos that harbors life, or provides the necessary conditions for it? To study the potential habitability of an exoplanet, it is crucial to decipher the exact composition of its atmosphere. Only in this way can we make statements about its friendliness or hostility towards life forms on other celestial bodies. And indeed, the James Webb Telescope is about to reach an absolute milestone in this respect. Thanks to these spectral data collected, experts have been able to analyze the atmosphere of an exoplanet more precisely than ever before. This astronomical breakthrough represents a sensation that previous versions of the Webb telescope had failed to achieve due to their technical limitations. However, that is now a thing of the past, thanks to Webb's near-spec spectrograph and its advanced instrument. When a planet passes in front of its host star, the atoms and molecules in its atmosphere leave absorption traces in the light spectrum. A fascinating example of this is the gas giant WASP-39b, located about 700 light-years away. This planet shows us how revealing the investigation of these transit signals can be. Since WASP-39b exceeds mighty Jupiter in size by a factor of 1.3, analysis of its gaseous envelope has been especially revealing. In addition to previously recorded deposits of water and carbon dioxide, Webb's instruments have also revealed the presence of sodium, potassium, and carbon monoxide in the planet's atmosphere. At the same time, it has been discovered that the atmosphere of WASP-39b does not appear to contain methane, which is in significant contrast to some of the gas giants in our own solar system. These acquired spectra offer particularly interesting information. The experts discovered an absorption line that initially cannot be identified in a known context. However, by comparing it with models, it was concluded that we were in the presence of a molecule never before observed on an exoplanet: sulfur dioxide. This finding and its implications are especially significant since sulfur is commonly found in gas giants, mainly in the form of hydrogen sulfide. This may provide clues to the formation history of the extrasolar world in question. Consequently, the unexpectedly high content of sulfur dioxide, together with the ratios of other elements to oxygen, suggests that the atmosphere of WASP-39b contains up to 30 times more heavy elements than the Sun. In addition, its low volatile element content is also relevant. According to our current models, gas giants form from the collapse of dense gas clouds into protoplanetary disks. The high proportion of light elements in the atmosphere of WASP-39b indicates this formation context. However, the situation is somewhat different in terms of solid matter enrichment. Based on the information obtained, it is concluded that this extrasolar gaseous planet probably formed in a similar way to Jupiter and Saturn, which offers an interesting perspective on its origin. Initially, a solid planetary core was formed, which then accumulated large amounts of gas due to gravitational force. The data provided by the James Webb Telescope mark an important turning point in exoplanet research. These data provide us with new insights into the evolution, chemistry, and physics of alien cosmic worlds, and will possibly contribute to the search for extraterrestrial life in the future. Looking back, as mentioned above, unlocking the secrets of extrasolar planets is just one of the exciting research goals that the James Webb Telescope has tackled on its journey through space. Understanding the origins and characteristics of the universe's first stars and galaxies has also long captivated scientists. The first images captured by Webb already confirm its success in this task. The researchers have identified several formations that may be the oldest galaxies known to date. With a redshift of 13.1, the possible Glass Z13 galaxy could have emitted cosmic light approximately 300 million years after the Big Bang. However, verifying the age and nature of candidate galaxies requires detailed spectral data. In the past, these data were lacking, but thanks to the James Webb Space Telescope, they've been collected and revealed for the first time ever. This telescope has provided spectral data for 250 ancient galaxies, and 4 of them have been found to have exceptionally high redshifts. The oldest galaxy of all, named Jade's GS13-0, existed approximately 13.5 billion years ago. So far, some characteristics of the earliest galaxies have been identified, which were relatively small clusters with a star formation rate of 1 to 2 solar masses per year. However, it is important to note that we're just beginning to unlock the secrets of this early universe. Experts have already discovered several additional primordial galaxy candidates that will need to be spectroscopically analyzed in the near future. Now, we would like to hear your thoughts on these groundbreaking ideas and discoveries that the James Webb Telescope has revealed to us. Leave us your thoughts in the comments, and don't forget to like and subscribe to stay updated. Thanks for joining us, and see you next time.